this webinar on laser applications in ZMAX OpticStudio. My name is Mark Nicholson and I'm going to be your guide for this whole session. In terms of user interface, everything that we're going to be doing today, or almost everything, you're going to find in the Analyze tab of OpticStudio in the Laser and Fibers group. And we're going to be looking at Gaussian beams and then at physical optics in the beam file viewer. We won't actually do much with the fiber coupling on this webinar. That's covered elsewhere in other webinars and in other knowledge base articles. First off, and as a sort of frequently asked question, all the examples and these PowerPoint slides are in a zip file that we can mail to you after the webinar. So don't worry about being able to keep up or take notes, because we'll send you everything that you're seeing here today. Then, the way that laser beams are often modeled is simply as collimated ray bundles. And this works well in a lot of cases. The trick is to know when it doesn't, and that's really what this webinar is going to be discussing. But for things like interferometers, common path or shearing interferometers, this is probably the most common application for the laser as collimated ray bundle approach. And it basically treats the laser beam as if it was just a bundle of parallel rays. And it's most commonly done using non-sequential ray tracing, although it gets done in sequential as well. And here is an example in non-sequential ray tracing where we model a Michelson style interferometer. We have two windows here with 50-50 coatings on them. We have two mirrors, and one mirror is very slightly tilted with respect to the other. And as a result, when the beams recombine, they overlap and interfere, and we get fringes as a result of that. As another example, and one which I'll just do a little bit more example on, just think about a laser beam expander. And this is a classic kind of thing that you would use rays for. Rays are coming in from the ray bundle that is a particular size over here. It's easy. There we go. There it is. So the rays coming in from its ray bundle over there, and then it's going to another lens, and then it's going into a beam splitter, which is giving front and back reflections. Now this beam splitter is a little bit subtle, and if we look at it in the editor, you'll see that it's got a very slight, you can't really see it in terms of a visual layout, but if I just click on the back surface of the window and right mouse click, I can get all of its properties, and you can see here that there is a very, very slight wedge angle that's been placed in X on that. So if you want to look at the same thing here, you can do that. Just click on it here and it shows you this in here. So if you look at the front surface has no wedge at all. The back surface has this very slight wedge angle, and in terms of positioning, it's positioned at 45 degrees in the beam. So we then take the reflections from front and back face and we interfere them. And because of the X tilt, we get interference fringes. Now, if you see here, you can see like two overlapping circles. The degree of overlap is due to the thickness of the beam splitter, but the fringing is caused by the tilt angle of the back face of the shear plate. And this is the beam perfectly collimated. We've got the separation between these two systems is exactly what it ought to be. And here we have it, 205. If I make that 203 so that the expander is slightly out of focus and the beam is now emerging, slightly diverging, if I repeat the ray trace now, then you can see how those fringes rotate, and they rotate slightly clockwise. If I put this down to 207, And so the expander, oh sorry, that's slightly converging light, I beg your pardon. 207 is slightly diverging light. And if I repeat the ray trace now, you'll see the fringes rotate in the opposite direction. And this is, of course, is a classic measurement technique for laser beam expanders. But this is just an example of modeling a laser beam in Zemax. It just uses the individual rays. We just coherently add them up. Works just fine in a really wide range of applications. But when do rays not work? And to understand that, we have to think about Gaussian beams, and then we'll also think about not perfectly Gaussian beams. And we're going to build a great example that demonstrates where simple ray tracing doesn't work and where we need to use physical optics instead. And that's going to be a spatial filter with a non-Gaussian beam being presented to it and a Gaussian beam being put out the output face of it. Before we get there, let's just think about what Gaussian beam theory is. Gaussian beams are an alternative to ray tracing. It's a purely paraxial model, so there's no aberrations considered by Gaussian beam theory. And a Gaussian beam is defined by any two of three parameters: wavelength, beam waist, and divergence. And they're controlled by this expression, and they're often used to study TEM00, perfect Gaussian laser beam propagation. And here's a schematic of what happens when you bring a Gaussian beam to focus. And you'll see the key thing is that a Gaussian beam cannot actually come to a point image. It's not possible to produce a point image of a laser beam. Instead, the smallest area that the beam will form is a region that we call the beam waist. And by convention, we refer to the waist as the half height of the beam measured from the z equals 0 point. So that gives us a beam waist, which is the minimum spot size that we can achieve. The next concept is the Rayleigh range. And the Rayleigh range is the distance over which the beam size has increased by √2 times the beam waist, or about 1.4 times the beam waist. And you'll see that inside that Rayleigh range, the beam size is not a simple straight line. Now, if you think of this as a point source with some divergence angle omega, or theta rather, then at large z distances, the Gaussian beam does look like a point source, and its size increases linearly with distance. But inside the Rayleigh range, the size variation is more complicated. And we refer to this, or one of the things that we use to refer to this is the phase radius of curvature. The phase radius of curvature is infinite here at the Rayleigh range. In other words, if you were to differentiate the wavefront, everything would be pointing along this direction. It comes to a minimum value at the Rayleigh range, and then as you go off to infinity, the phase radius of curvature goes infinite again, and it's given by this expression. And the Rayleigh range itself is given by this expression. It just depends on the beam waist and the wavelength. And this is what makes a Gaussian beam so interesting, is that as you come to focus, instead of just following the straight lines down to a point focus, instead the wavefront self-interferes and it prevents a point focus from being formed. And as a result, we get the fundamental differences between rays and Gaussian beams. Rays always travel in a straight line and they can be brought to a point focus, whereas a Gaussian beam doesn't really it travels in a straight line along the z-axis, but if you're measuring the width of the beam within the Rayleigh range, it does not scale linearly with distance. And so Gaussian beams diffract as they propagate, and so the beam changes size and its effective divergence as the beam propagates. And then if we add in a thin lens with some power, then we simply transform the phase radius of curvature as given by this expression. But we still maintain a spherical phase radius. So no aberrations get added. And this is where physical optics adds the capability to track aberrations as well as to add in diffraction from arbitrary apertures. And people often think of POP as being important because of the aberrations, because of the apertures and the ability to handle a diffraction from an arbitrary aperture. But it's really important when we look at laser beam propagation from the perspective of being able to see the phase distortion of the laser beam, and as a result to see how m squared varies, even though maybe nothing in the beam is actually aperturing or clipping the beam. So we're going to do an example here, and we're going to start off with a helium neon laser beam that is at the red Heaney line, beam divergence of 2.5 millimeters, sorry, beam diameter, I beg your pardon, 2.5 millimeters, and a divergence of 0.175 milliradians. And then 10 millimeters after this laser, there's going to be a 5 millimeter thick NBK7 lens. The image plane is going to be 50 millimeters beyond that. And our problem is to design the lens that gives the smallest Gaussian spot size at the image plane. And there's an important point here. The beam diameter, as the beam emerges from the output face of the laser, is not to be confused with the beam waist. Typically, the beam waist and the output port of the laser are two separate things. So some resonator designs do place the waist at or near the output port, but they're not in general the same thing. And typically, they are the beam waist for a Fabry-Perot type of laser, like the helium neon tube laser, the beam waist can be meters behind the output face of the laser. And in the Gaussian beam calculation within OpticStudio, we always define the beam waist relative to surface 1. Now, it doesn't have to be surface number 1. We just have to position the waist relative to surface 1. So here's our first step. We're going to define the laser, and we're going to do it like so. I'm going to actually open up one of the sample files that I'll be sending through to you if you're interested in it. Going to save that. And it's simply this system set up. I've given an entrance pupil diameter of 6 millimeters, just so that we actually get some rays showing on the screen. And the wavelength is set to the helium neon red line. And I have defined surface number 1 to be the beam waist. And I've defined surface number 2 to be the output port of the laser. And that's, that's almost it. The next thing to think about now is how I define the Gaussian beam. Now, the Gaussian beam's beam waist is computed with lambda and the tangent of the divergence angle, and that gives me a 1.15 millimeter value. So the waist is 1.15 millimeters, and the beam, when it's emerging from the laser itself, is 1.25 millimeters. So the beam has grown as it's propagated, and we need to compute what that distance is. And so what I've done is I've set up the beam waist at some distance from the output port, and I want to see what kind of size the beam is as it propagates out the output face. So to do that, I'm going to go to my Gaussian beam, paraxial Gaussian beam calculation, and we're going to set it up like so. I'm going to set the waist size to be 1.15. I'm going to make surface number 1 the waist, so this surface 1 to waist distance is 0. And I want to look at the beam size on surface number 2, which is the output port. And you'll see that this acts like a little calculator, and it tells me that the waist is 1.15 millimeters. its position is 100 millimeters away, if you see here, and the beam size is just over 1.15. So I can play with this by hand and make this 200 if I like, and just have a look and see how much bigger the beam size gets. It got a little bit bigger, but not very much. Or I can do it the smarter way and have Zemax actually do the calculation for me. So you can see I've set this up as a variable. So that's got a V for variable. And just to be consistent with the notes, I'll put that back to 100. And if I now go to the Optimize tab and open up the merit function editor, you can see what I've got in the merit function editor is an operand called GBPS, Gaussian beam paraxial size. And it starts at surface number 2, or it was set rather at surface number 2. The beam waist is 1.15 at a distance of 0 from surface 1. And I want to target the beam size to be 1.250 millimeters. And you can see that it's currently 1.15013. I'm only showing 3 decimal places here. So all I need to do is optimize, press the start button, the merit function goes to effectively 0 straight away. And you can see here the distance that I have between the beam waist and the output port. You can see here that the beam size is exactly 1.25 millimeters at the output port. 5 millimeters away, it's grown by an additional 3.4 microns. And just to make this plot easier to look at, I'm only going to draw from the output port onwards. So that now this looks like so. So that set up my my beam waist. I'm going to take the variable off of that. I'm going to go back to the notes, and that just goes through exactly what we've covered. I won't talk through those slides. It's just everything that we've done. The automatic optimization. And now we're going to add the lens. And 10 millimeters away from the output port is a 5 millimeter thick lens, and then there's a 50 millimeter distance to an image surface. So to model that, I'm just going to click on surface number 3 and press insert. Gives me 2 surfaces. That distance there that is currently 5 should actually be 10. There should be a 5 millimeter NBK7, and this should then be 50 millimeters. And just to make this draw a little bit more easily, the semi-diameter margin I'm setting to be 1 millimeter. And it just means that the components all draw larger than the beam that this beam drawn is. And I've now fixed this number, so I don't need to change it. But what I want to do is optimize these 2 parameters. So I make them variables with Control Z. And I'm going to go back to my merit function. And instead of looking at surface number 2, I'm going to look at surface number 5. That being the final surface. And instead of a target of 1.25, I want a target of 0. I want the smallest spot I can have. And if I just update that, you'll see the merit function is no longer 0. Actually, it's the same as the beam size. And if I just hit optimize, start, bang, down it goes, and I get a value of 8.3 microns. So you see here the beam size as it leaves the laser is 1.25 millimeters, but now as it lands on the surface, the image surface is 8.3 microns. So that's given me a nice focused laser spot, and this lens would be very, very good for focusing a lens like a laser like this one. So again, the notes just go through everything there that we've set. The problem with Gaussian beam calculations is that there's not much else you can do with it. It gives you things like beam waist and phase radius, Rayleigh range and such like. It works in spherical and cylindrical systems, but it doesn't really give you any other useful information. And it doesn't let me say how much wavefront distortion that lens has added to the laser. So this is where physical optics comes in. And I'm going to set up physical optics like so. I'm just going to get myself in the notes to the same point as we're at. Yes. And I'm going to set up physical optics now to do the same calculation. So I'm going to go back to Analyze, Physical Optics. Drop that down. Just push it up here so we can drop that down. I'm just going to turn Auto Apply off so that it doesn't apply as I'm talking, because that can be useless. And I'm going to start the beam at the beam waist. I'm going to propagate it through to the image surface. Under beam definition, I'm going to use a Gaussian waist and a sampling of 128 by 128. And the beam waist is going to be 1.15. Oops, 1.15. 1.15. And then for the overall size of the array, I'm just going to press the automatic button and that will size the array for me. And I'm going to tell it that I want to see a cross section in X of the irradiance as a result of doing it. And now that's all done, I'll apply that. And there is my beam. In fact, I've got a 4x zoom, and let me just take that off. Apply that. So there's my Gaussian beam on the image surface, and you can see the pilot size is about 8.3 microns. If you can just read that little part of the text there. It says pilot size is 8.3 microns. A nice looking Gaussian beam, but let me now show you the phase of the beam. And here's the real reason for using physical optics, is you can now see the distortion of the wavefront of the beam as it goes through this lens. And you can see a couple of things very, very clearly here. You can see here's the focus that's being introduced by the center of the lens. You can see the spherical that's trying to compensate it as you get towards the edge of the lens. And you can also see the Gaussian shift, which doesn't normally really do a whole lot, but it's just a piston term that offsets the phase at the center of the beam. So I've just used physical optics very quickly there to propagate a Gaussian beam through the optical system, and I've been able to see the irradiance and the phase of the beam as a result. So it's really cool. You can see all of that, and by the end of this webinar, you will know how to measure the m² of this beam, and I'm leaving that as a task for the viewer. Is once you get these sample files to measure the m² of the beam after the webinar, we're going to cover how to do that. But what we're going to go into now is a spatial filter, and a spatial filter uses the lens to focus a beam onto a pinhole. At the focal plane, we're effectively taking the Fourier transform of the complex amplitude of the beam. The small pinhole allows only a fundamental mode to pass, and so the output is a Gaussian intensity profile with some low intensity rings around it. And let's just have a look. Again, I have a file set up for this, and it's example 5. Set up. And here it is. It's two lenses. They're achromatic doublets, and we use achromatic doublets because the center surface is still used to control spherical, so it gives us a very good imaging performance for an application like this. You can see also from a point of view of the rays, I'm using a Gaussian apodization just so that it looks more like a ray trace, and looks more like a Gaussian beam when it's ray traced. But that done, I'm now just going to hide the System Explorer. It's not really relevant to us. And let's just have a look at the physical optics propagation window. And first of all, I'm starting from surface 1. There's and that's my beam waist. But surface 1 this time is defined as this donut beam, and this is a multi-mode file. I don't really have time to explain multi-mode files on this webinar, but this is an addition of a TEM 10 and 01 mode, and it gives me this kind of distribution, a donut type ring with a 0 of intensity at the center of it. And then I'm propagating that all the way through the system, from surface 1 to the image, displaying it all the way through the system. And you can see that I'm also saving the data on all surfaces. So over here I have a beam file viewer, and this is currently, let me just make this larger. You can see this is looking at surface number 1. And if I just give this window the focus, I'm using the left and right arrow keys, and as I press those arrow key buttons, actually, I beg your pardon, I should just need to make this, did I close that? Sorry, I just need to recalculate that, so I beg your pardon. And now I will pick up the beam file viewer again. And here it is. I want to zoom in by a factor of 4. And now if I just use the right arrow key, you'll see that I'm propagating surface by surface through the system. So here I am now at surface 5, which is where the pinhole is going to go. It isn't actually there yet, so surface 5 and surface 6, which are co-located, look identical right now. And you probably can't see with the color resolution of the webinar software. So let me just use a log scaling to show that the intensity actually goes out all this way. Again, if this were a Gaussian beam, you would expect to see a Gaussian focal plane, but you're actually getting something much more complex than that. And if I just look at this as a cross section in X, you'll see that I'm getting a minimum of intensity at around about 5.6 microns, something like that. And then intensity comes back up again and goes down. And it's my intention to spatially filter this beam so that we allow only the Gaussian portion of the beam, the fundamental mode through the system. So let me then just go back to showing this as false color. I'll take the log scaling off. And then we just come back up and we propagate through the rest of the system. Here's the lenses. And then we come to the final surface, surface number 10, and we have reconstructed the donut that we put in. So in other words, we've put a donut in and we've got a donut out. That's just talking us through everything there. Now, Siegmund's m² factor is a great way of diagnosing beam quality, and we can use it first of all as a diagnostic for any beam and also as a target for optimization. And the definition is that a beam with an m² of 1 will change size as you propagate at the same rate as a TEM00 Gaussian is, and any other beam has an m² bigger than 1, and so that will diffract faster than a perfect Gaussian beam would. And m² is a so-called output characteristic. The beam can't be defined by its m². So there's an infinite number of beams that have a waist of 0.5 millimeters and an m² of 1.3. So you can't uniquely define a beam with its m², but you can measure the quality of any beam with its m². How do we get it? Well, we get it using an optimization operand called POPD, and it stands for Physical Optics Propagation Data. And it returns all the beam characteristics that are required. And it will give us things like the pilot beam data, the centroid locations, effective widths, m squared and x and y, and so on. And so what we're going to do is to configure this is we're going to press the save button on the pop settings dialog, and that saves the current settings of the physical optics propagation calculation. And then we're going to open up the merit function. So let me just press save on here. And then I'm going to open up the merit function, and you'll see I've pre-built the merit function. And it uses the pop D operand. Item 23 gives you the x width, item 24 gives you the y width, item 25 gives you the m squared in x, and 26 gives you m squared in y. And of course, as this is rotationally symmetric, we expect them to be the same. So we use it first of all looking at surface number 1, wavelength 1 and field 1, that's all there is in this system. And we've got a beam width of 1.414 in x and y, and an m squared of 1.431 in x and y. We then get the same data on surface 10, and the beam is slightly larger. It's 1.418, so it's only larger by 4 microns, but the m squared has now worsened, and it's now about 1.753. So that's the beam radius and m squared just propagating through these beams with nothing actually happening. I have no pinhole or anything like that in there yet. So what we're going to do is we're going to add a pinhole at surface number 5, and I'm going to set its aperture to be about 5 microns. And I do that because when we looked at the irradiance, it minimized at about 5 microns. And we want to, as well as cut the beam down, we also want to minimize the amount of diffraction that's introduced by the pinhole. So that's why I'm choosing a 5 micron distance. So let me just go back to Zemax OpticStudio and go back to the lens data editor, which is hiding here. And on surface number 5, which is the pinhole, I'm going to double click, I'm going to go to the aperture tab, and I'm going to set on it a circular aperture with a maximum radius of 0.005. So that's 5 microns, and I'll just click away from that and it will be accepted. I can actually close it now. And if we repeat the physical optics propagation calculation now, you'll see that the output beam has now become circular. It's lost the donut that we were starting off with. Again, let me just go back here to the starting. We're going to go through this surface by surface. So there's the donut of the input beam, and I propagate through surface 2 and then 3. Oops, I haven't got focused. Through surface 2 and then 3 and 4, and then I come down to surface number 5, which has now got a pinhole on it. And if I just show this again as a cross section, nope, sorry, that's here, cross section in X, and I'll show the log scaling. Then you can see how the beam is being truncated right at that point. And then I go on to surface number 6, which is co-located, so the beam looks completely unchanged. And so I'll now just go back to my false color and linear scaling. And you can see that as it propagates away from the pinhole, I've now got a central kind of lobe structure. It comes up like so. And here's now my output beam. And let me look at the cross section of the output beam. Cross section in X. And that looks much more like a Gaussian beam should look like. Remember, I'm putting in that multi-mode distribution, and I'm getting out a distribution that looks Gaussian. So just how good is it? Well, let's have a look at the merit function again. Now that we've done that, if we recalculate the merit function, you'll see that the m squared of this beam is now 1.25. So the m squared of the beam is now smaller than the m squared of the input beam. So we've cleaned that beam up considerably. The question is now, can we actually make the m squared even better? You know, can we optimize the m squared now? And the answer to that is yes, we can. The things that we want are the distance from the focusing lens to the pinhole, so we can get that optimized for the starting distribution. We get the tightest focus on the pinhole, and then the size of the pinhole can be varied. And our goal is to get the smallest m squared value. So our variables are the thickness of surface 4, which is already may well have been set already. Let's just have a look at that. Yeah, so there's the thickness of surface 4. And then I also want to make the radius of this aperture that I've placed on surface 5 variable. And there's a sneaky way I can do that. In principle, because it's not an editor parameter, it's not optimizable, but I can cheat. And I'm going to use the operand APMX, aperture maximum, on surface number 5, which is the pinhole. And I'm just going to make that a variable. So there we have it. So I managed to sneak my pinhole aperture into a variable rather nicely. And now I'm just going to go back to the merit function. And all I need now is the minimum size of the beam on surface 5 and the minimum m squared on surface 10. So let me just do that right now. So I'm going to go back to here, and I'm going to just delete all these operands, and I'm now going to just insert a couple of new lines, and I'm going to get smallest beam on surface 5 as one of my goals, and I need that to be pop D. Surface number is surface number 5. Wavelength is wavelength 1. Field is field 1. The data item that I want on this is 23. That's the X radius. I want to target that to 0 with a weight of 1. And then I want smallest m squared, m2, on surface 10. And to do that, I'm going to use pop D again. But this time on surface 10, use 1, 1 again. And this time I'm going to use parameter 25, which is the m squared parameter. And I'm going to target that to be 1, the weight of 1. So one is targeted to 0, make it as small as possible. The other one is targeted to 1 because m squared can only go to 1. And I'm now going to just call the optimizer. And because I've only got 2 variables in here, and they're both strongly coupled, I'm going to use the orthogonal descent optimizer. I'm going to just use 1 cycle of optimization just for speed in this example. I'm going to fire that off. And this will take a few seconds. Okay, so that took about 42 seconds. I'm just going to exit from that, update here, and you'll see now that the m squared has improved to a value of 1.04. So that is very, very nearly a perfect Gaussian. So I'm now getting a really nice Gaussian out of this system. Not only does it look like a Gaussian, but if I look at the phase going across it, you can see that that's a far better looking phase distortion. You can still see there's focus and spherical, and a little bit of Gaussian shift as well. But I've done a really good job in optimizing that m squared. It's come in just where I wanted it to be, and only just slightly greater than 1. So I've designed a really good spatial filter here. I can also do things like I can tolerance the spatial filter and say, well, what happens if the pinhole size varies? What happens if I'm out of focus and such like, and see how the m squared varies as a result of that. But I don't have time to do that at the moment. So there we go. So in summary here, rays are a great first pass at how laser beams behave, but they do have some limitations. Paraxial Gaussian beam adds extra information, but it ignores the aberrations. And physical optics gives the best of both worlds when rays are not adequate, because it lets you look at the phase profile of the beam, and it also lets you quantify that in the most meaningful way that is used in laser physics, which is by m squared. So we discussed a shearing interferometer, and just showed you how to use straightforward rays to model, in that case, the collimation of a laser beam. Worked perfectly. We looked at a simple lens that we optimized for Gaussian beams, and we got some residual phase aberration when we used POP to look at it. And then we used a spatial filter, and we could look at the input beam's m squared, which was about 1.4 or something like that. We just put a filter in and hoped for the best, and that got us down to about 1.2. And then we optimized the system, and that got us down to 1.04 in m squared. So, physical optics, when it comes to the design of laser optics, optics which are intended to image or focus or modify a beam, very, very powerful capability.